All right, guys. We're going to officially get started here. So, first of all, hello in person. Good to see new faces and returning faces. I am glad to have met you guys a little bit. Some of us we talked a little bit before class, so it's good chatting. We are going to be finishing up this chapter 11 today. And again, reminder that the content for chapter 11 is going to be due at the end of this weekend. It is set to Sunday. I know it's a holiday weekend, but just remember that I just have set the due dates to be Sundays for thus forward. So it is Sunday at midnight to make sure you get that in. So if you are at all still having problems with like McGraw-Hill or anything, make sure you please chat with me so that we can get you squared away for this weekend. We have been talking about a set of scenarios in reactions in which there is something called conjugation. Remember, we were talking about these allylic systems and how allylic systems can be formed during certain reactions, and because of their formation, because of their conjugation, they allow for additional resonance, additional stability, and thus in certain reactions cause extra products to occur because of those scenarios. I talked to you about how in the scenarios of allylic systems, there are 3 different potential scenarios where you can have a radical next to a double bond, a positive charge next to a double bond, or a negative charge next to a double bond, causing that extended pi orbitals. I mentioned to you also that this can occur if you just have alternating double bonds, right? And you can get this to keep going, essentially, for as long as your molecule is. If you have alternating double bonds, you'll have conjugation. Again, one of the shorter versions of this is what we would call a diene. A diene, as you maybe can guess by the name, is just di for 2, and then ene, remember, ene means double bond, right? So this is just a scenario where you have 2 double bonds. Of course, if you had 3 double bonds, it would be triene, et cetera, et cetera. We're just saying 2 double bonds. You can have 2 double bonds in a lot of different scenarios, right? It's not only this particular scenario where you have conjugation. So I'm just showing that dienes can occur in lots of scenarios. All that it means is you have 2 double bonds in a molecule. It can be conjugated. This first example right here is an example where you have a conjugated diene. That's, notice, double bond, single bond, double bond. That causes there to be pi orbitals, and so like this. See, at each of the points where the double bond starts and ends, there's a pi orbital. And if you look at that all together, all the way through from end to end of each of the double bonds, you have pi orbitals that can be shared. They could be isolated. That just means that their pi orbitals are not able to overlap. So you can imagine here and here, see how there's too much space between them here. Still a diene, just this one doesn't have conjugation. They can also be what's called cumulated, although these are rare just because it's hard to stabilize these, but this also does have some shared pi bonds. Get this to come on, computer. Right, my pen and now I'm trying to do it with my finger. let's just do with my cursor. It's gonna look kind of ugly. But they're here and here and here. So yes, there is still a shared pi system in a accumulated. You'll actually notice that here it's kind of like scrunched up. Still two double bonds, but notice in the conjugated one, you actually have best case scenario where they're kind of spread out enough, but you still have overlap. So quickly just touch on this, just touch on naming, because as we go through all of these functional groups and talk about these functional groups, we'll talk about how to use their IUPAC name. And that includes diene. So hopefully just a refresher on naming double bonds in general. So let's start with what's the longest continuous chain here that you can count? How many carbons long? 7. So I'm gonna say like 1, 2, 3, 4. Use my cursor. 4, 5, 6, and then you could go either way here. This is equal 7. I'm gonna say here is 7, but those are equal to each other. Okay, so 7 is what? Can anyone tell me what we use? What prefix do we use for 7? Hept, right? So this is some hept something. Hept, and where should I start this chain? As far as like, where should my number 1 be? On the left, right? So here, as far as functional groups go, the double bonds have priority. We want to number giving them lowest numbers in general. Also, remember all side groups, we want to try to give them lowest numbers possible, but while thinking about priority of certain functional groups. Again, the double bond has priority, so we're going to start closest to where there's a double bond, which is on the left side. Okay, so I like to take this, from the kind of base parent name and then add all the other additions on. So you guys already said this is a hept. What would the rest of that name be? Hept what? Hepta, so we would say hepta diene, right? So normally if it was one double bond, you might have just said heptene, right? This is going to be hepta diene. Now, make it tough for me with my cursor not. Really want this to work. Let's see. Come on. Come on. Sorry, guys. I left my good pen at home and now we're suffering a bit. Hepta. Okay. So heptadiene is what we would name this, but there's one extra component here. Now that I have 2 double bonds, even if I had 1 double bond, you usually have to tell the reader of this information where they are, right? So where would these double bonds be? The first one's on what? At 1, right? So, well, what about the second one? So it'd be 1, 2, 3, 4, 5, starting at 5, right? We're always going to list where they start. So this is going to be hepta 1, comma 5. Diene. Oh my gosh, I really hope I don't have to write as much stuff for you guys tonight. It's really painful in my cursor. Okay, hepta 1,5-diene, that's the base name of this chain. There are other things on it. Can anyone tell me some other side groups on this? Fluoro. And methyl, okay. And that's it, right? Does anyone see anything else? Here's a methyl, and here's another methyl. What number is this chlorine on? 5, so that would be 5 fluoro. Sorry, C for F. And then we have 2 methyls here. How do we deal with if you have more than one functional group? Well, we just did it, right? Di, right? So this would be a dimethyl, and just like with our double bond, you have to put both numbers. What numbers are those at? 3, 6. For those of you who had entered, I apologize. I left my good pen at home. I was saying I hope we don't have to write as much stuff tonight. I think I don't, but you're gonna have to suffer with me on this. Sorry. Dimethyl. Okay, these would go in front of the base name, right? And they do go in front of the base name in a certain order. What's that order? Yeah. Alphabetical, right? It's not, doesn't have anything to do with their numbers, just alphabetical. So this would be in what order? The chloro and then the methyl. So all together, this whole name, I'll even. Would be first the 5-fluoro, 5-fluoro, 3,6-dimethyl, hepta 1,5-diene. That would be the, yes.
Could you also do 1,5-heptadiene, or do you have to put it in?
Good question. So I do it this way just because this is the IUPAC way, but it is acceptable, and I always accept it, when you are naming any functional group that is part of the parent name. Like in this case, where the ene is part of the parent name. You can put the numbers in front of the parent compound name. So you also could have written that 5-fluoro, 3,6-dimethyl, 1,5-heptadiene. Yes. I like to just put the 1,5 in the middle. Personally, to me, it makes more sense because I'm seeing exactly what the numbers are attached to. They are for naming that functional group, the ene, but both ways are accepted. All right, so just doing that practice, hopefully this is a good warm-up, remembering how to do our naming, numbering. And also you're seeing the dienes. That was the new component here. So let's talk about dienes a little bit more. What about their stability? Generally speaking, if you compare a diene to just an alkene, what I'm talking about is just one double bond. They are less stable. They're destabilized compared to just one double bond. So 2 double bonds, a little less stable than 1 double bond. On here, we're looking at an energy diagram of both pentene. 1 pentene's all the way on the left. You can see 1,4-pentadiene, 1,3-pentadiene, and then 2-pentaene. These are all different. So here's one with just 1 double bond. This is also 1 double bond. On the right. And up at the top, we have a diene here and a diene here. Both of the dienes, if you're just looking at compared to having 1 double bond, that higher energy, that's actually less stable. They're less stable. But if I'm comparing diene to diene, notice one of them is just a little bit more stable than the other. Which one is that? The conjugated one. So although both of the dienes are less stable than if you only have one double bond, and much less stable than if you have 0 double bonds, which we're comparing pentane all the way here at the bottom, which has no double bonds. Having conjugation stabilizes it a little bit more. There's the theme you guys hopefully are seeing here. When you get conjugation, resonance, it adds some stability to the compound. All right, here we're asking about the weakest carbon hydrogen bond in this diene. So I want you to think about this is a slightly hard concept, but when I'm saying weakest carbon hydrogen, what I'm asking is if I were to remove a hydrogen from this compound. First of all, if I take a hydrogen off of it, what is left in its place? If I take a hydrogen off of a carbon, what happens to that carbon? Positive charge. Okay, so keep that in your mind. Think about all the other things we talked about before. What I'm really asking is, what's the best place to put a positive charge here? When you say the isolated one, what you mean? You try to use the numbers up here. See that they numbered the carbons? This is 1, 2, 3, 4, 5, 6, 7, 8. Which of those spots would be best to have a positive charge appear on it?
Would it be number 4?
Yeah, I think that's what you were saying. I just wanted to make sure that this is, and why do you guys think number 4? It is isolated, but if I made it into a positive charge, what happened? What happens to it then? So remember, here's a pi, here's a pi. Currently, or before I put that positive charge there, they were isolated from each other, right? But what happens, this is next to 2 double bonds. And if I pluck off a hydrogen and put a positive charge there, now I have a pi orbital and I can connect all my pi orbitals. Just to be clear, I want you guys to think about, this is thinking about the allylic systems too, right? That's the whole point of the allylic system. If I make a positive charge, negative charge, or radical next to a double bond, it now makes a pi orbital next to it and extends those pi orbitals. So that also means that, for example, this spot is pretty good too, right? If I were to put a positive charge here, I would get 3 together. So that's pretty good. Same thing over here on number 1. If I were to pluck off a hydrogen here, I would have gotten a positive charge here and I would have gotten 3. But you can see that the best spot on this particular compound is in the middle, because then you get all 5 together. You would get 5 overlapping orbitals instead of just a 3 or a 3. You guys see that now? Yeah. So weakest carbon hydrogen bond, meaning best place to pluck off a hydrogen, is at carbon number 4, because it would have resonance, it would have conjugation, it would be the most stable if you happen to do it at that spot. None of them are going to be that stable, but that would be the most stable, which is why it's going to be more likely. So when we're talking about diene stability, I already kind of showed you a plot about dienes and their stability. We already noted that if we're talking just about dienes, If you have a conjugated one, it's going to be more stable than just an isolated diene where they're not conjugated. But I hadn't noted this point, which is that alanines, which are what I showed you when you have double bond right next to each other. So no space right up on each other. And allene is the least stable. I had kind of said, oh, we don't really see these that much. They don't form as much. They are the least stable. They are already hard to form. It has to do with how strained the carbons end up being, because you have a set of 3 carbons that are essentially set as linear. And they can't really bend or move because of that double bond. All right, so let's talk a little bit more about bonding in these conjugated dienes. The single bond that connects a conjugated diene. So again, I'm talking about ones where you do have conjugation. That's the single bond that's between the double bonds. Double bond, single bond, double bond. That single bond, specifically the one between the double bonds, is shorter than most single bonds. Anyone have a guess why that is? Maybe on the slide. It has to do with the fact that there is conjugation happening. Conjugation means that we're sharing. It's actually becoming almost like a resonance system in which the double bonds aren't particularly staying in their one spot and they're kind of shared overall. So that single bond is suddenly not really necessarily a single bond, and those double bonds aren't necessarily a double bond. They're all kind of sharing together, so they become kind of a mesh of each other. So that particular single bond is a little bit shorter, more like a double bond. Double bonds are shorter than a normal single bond. It becomes a little bit like in between. Again, because we're having this resonance, it's kind of sharing, the system in that area is sharing between double and single bond. You can have rotation amongst the single bond. Just a reminder, double bonds, like if you're actually thinking of the double bond that is connecting two things, there's not rotation between them inside the double bond. And that's why we can have cis and trans double bonds, because they can't rotate, so they're stuck as either this way or that way. Where the single bond is in a conjugation can allow for some rotation, and so you actually can get these interesting phenomena in dienes where we have what's called S-cis and S-trans. So here we have on the left the S-trans configuration where the single bond has kind of rotated the double bond. So we're not even talking about like within the double bond what's connected to it, but we're saying like as far as the whole molecule of that whole system, you can have it being in this trans configuration, or kind of in this almost C shape where we've rotated the whole bond inside to a S-cis conformation. This, I'm not gonna, you guys don't have to name S-trans or S-cis, so don't worry about like, this isn't some naming configuration. What this is just interesting to note, because when we talk about a particular reaction later, and we talk about reactions of dienes, there are certain reactions that are going to prefer this S-cis conformation. In fact, you'll see me drawing it that way. You'll see them drawn in this particular kind of C-shaped configuration. The closeness that they have to each other allows for some fun chemistry that you'll see. Yes. The steric crowding that occurs in the S-cis, you mean? Yeah, so I mean, just if you just look at it, see how the hydrogens and other elements on there are just closer together. See, especially on the end here, I'll point out, like right here. I have to keep forgetting. Right here, versus, these are more spread out. So the S-trans configuration is more stable, and it's likely that in a normal configuration, they're going to be in this setting. But like I said, you'll see for some special reactions, the SS configuration is actually needed to kind of get everything close together, although it's all sterically crowded, to complete the reaction. Again, just a quick note on the allenes. This is not the diene, or it is a type of diene, but it's where you have the doubled up double bonds. As I noted to you, there are in this linear conformation where it's this straight line, they aren't planar, meaning that the elements on one end of the carbon and the elements on the other are not in the same plane. So it's linear, it's a straight line, but the ends of them are kind of twisted. This is another reason that they don't have good stability, because they are also twisting those pi orbital planes. So they are not lined up with each other. It actually is kind of dislocating the pi orbitals. So normally we would say, you have your pi orbital on your double bond here, but with these, because of how they have to sit, they end up being kind of askew from each other. You don't have good lineup, and then you don't have good conjugation along the pi orbitals to allow for electron flow. These do have some special stereochemistry because of their linear properties and because they're very fused and stuck in those settings. The groups on each end of the diene, so as you saw here, that would be the hydrogens and the hydrogens, are, if you think about it, almost like in a chiral carbon, right? You have two set in one plane, two set in the other. And so you actually do get chirality amongst those, whatever is attached at the end. Yeah. Again, if you had different substituents on those points, you could get chirality on them. Kind of truncate your view to think about it almost like that whole set of double bonds is one carbon, and then whatever is on the end could be our four different substituents where you could have chirality. Again, not something I'm going to make you guys name, not something you're really going to come in to encounter with, just something to note, some fun note on there about allenes is they have their own chirality. Okay, so let's talk about how you would make a diene. We've talked about how to make just alkenes already in Orgo 1. But what about if you want more than one double bond? Well, you can technically just do a dehydrogenation industrially to just go from single bonds to a diene. You can see this takes a lot of heat and a metal catalyst. However, in a laboratory, we often just do stepwise elimination. So here at the bottom, hopefully you can see we got an alcohol here, and we already have a compound with a double bond on it. And then we're just going to use elimination to prepare a double bond by eliminating that leaving group, the alcohol, where that alcohol was. You could also do this. This is on the left-hand side, looking at it using like an E1 reaction, and on the right-hand side, it's an E2-like reaction, just depending on what substituent. Here we have alcohol elimination, and here we have a halide elimination. again, going from an E1 side to, and then on this side, an E2 side, eliminating either a bromine or over here an alcohol to get a conjugated diene. So why though would they selectively make this product instead of eliminating at a different place? For example, I could have formed a double bond here. I also could have technically formed a double bond over here. Yeah, right here or right here. Notice essentially any point that those leaving groups are attached to, they could have eliminated kind of inward, which is what we're showing in the middle. Could have eliminated on that methyl group that was up, could have eliminated to back behind it. Technically, those are all potential eliminations in which they could have eliminated. But why is what you're seeing in the middle, which forms this conjugated diene, why is this what is mostly selected for? Why do you think? It's the most stable, right? Again, see the theme here? Because of the resonance and the conjugation that occurs during this process, it adds stability, and so it is often selected for.
A question. If
Yes.
resonance occurs, doesn't it mean that those forces?
We will talk about that in reactions that involve dienes. So that's more so elimination reaction. You could, the thing about that is, let me go back just really quickly to answer that question a little bit better. So one of these, first of all, is only eliminating through an E2, which does not form a cation. But let's just think about the E1 elimination that does form a cation. And you can see that essentially we're removing from here, right? And you form a cation here. At this point, though, there is no allylic system. You agree, right? There's no allylic system. We're not talking about an allylic system. We did talk about how if that exact scenario happened, but it was right next to the double bond, you would make an allylic system and you would have resonance and you would have multiple products. That was what we talked about in the past part of the chapter. At that point on the chain, there's no allylic system. Okay, so everything that's moving forward as far as then where the next part of the elimination goes, which the next step is remove a hydrogen and form your double bond. That next step is only just driven by the product being more stable if it forms a double bond essentially to its left, right? Okay, so at this point for this reaction, it's not, nothing is being driven by resonance here. When we have situations like in the earlier one where a cation is formed right next to a double bond, you would have resonance, you would have multiple products. Okay, I know, slightly confusing, talking about SN1 and E1s all in the same scenario, but this is just showing that the product here is driven by the product being more stable if it is that specific product. Okay, so we're going to talk about reactions on dienes. Now, this is where you're going to see some interesting stuff happening when I do reactions on dienes. Just like the other alkenes we've seen, the same reactions apply. You can do same types of reactions on dienes that you could just one double bond. In particular, we're going to talk about electrophilic addition. Right now, we're talking about addition with halides. So just a reminder, that's the idea of opening up a double bond. In this case, the double bond would be grabbing a hydrogen and a halide. You essentially open it up to form a hydrogen, and it will grab the hydrogen and the halide. These are a complex as far as their mechanism, but you're going to notice that when you have a diene system, the addition reactions can have various products. Why would that be? Now it's because of the resonance that will occur. So just showing when you're going through in one of these addition reactions, through the steps, a cation is generated. So first part is you grab the hydrogen, and we're opening up the double bond to grab the hydrogen. At this point here, we have generated a cation on one side of where the double bond used to be, and we have grabbed our hydrogen. Now, normally, if this was just a single double bond, then the next step would just go through smoothly. Chlorine would add where that positive charge is, and you'd be done with your addition. However, look what just happened. Just because of how dienes are structured, during the process of this reaction, we have created an allylic system. There is a double bond next to a positive charge now in the middle of this reaction. And what can happen if that occurs? Resonance. So this can resonate during the process of the reaction. Yep. During the process of this addition reaction, there is a cation that is generated next to a double bond. And if that happens, you can have resonance because this is an allylic system. It's showing you how the resonance can occur so that the cation can end up over here, switch with the double bond. Essentially, both of these are possible to exist during the process of the addition reaction, after the first step, but before the second step. So when you go to do your second step, you can have two products. Here's another example of that. This is the addition reaction of butadiene. So we're going to do an addition reaction on this double bond. During the first step, that double bond is going to open up and generate a cation right here. That would make a double bond next to a positive charge, creating an allylic system. These two things can resonate with each other, and both of them can exist. So you can have one that exists just like that, and you can also have the other version where the positive charge is on the end, double bond is shifted to the middle. When the second step goes to happen and we go to add our bromine, the bromine can either add in this version, or I'll draw out the other version. The other version would be positive charge here. Draw it here. Positive charge here. Double bond here. Here is the shifted version of that. So when bromine goes to add, it can either add to this version or to this version. That's why you would get two products. You get the original version we saw, and you also get this version. This is called giving you 1,2 and 1,4 addition products. We're using 1,2 and 1,4 because when we're talking about a diene, you can imagine wherever the diene is, the conjugated diene is in the compound. If we just isolate our view on the diene and we label from the carbon of the first part of the double bond as 1, 1, 2, 3, and this would be 4 right here. So again, I'm just thinking, I'm looking at whatever system it happens to be. I'm just looking at that conjugated diene, starting at 1 and then ending in 4 at the end of the second double bond. Then you can add in a way that adds in the 1-2 position along the double bonds or in the 1-4 position. We're saying the hydrogen and the bromine adding either 1-2 or 1-4. So this would be, they're actually thinking about it the other direction. This would be 1 here, 1-2 addition, and this would be 1-4 addition. Let me rewrite that. 1, this is. Okay, so both products can exist. If you start with a diene, you do an electrophilic addition. This is just another case scenario where an allylic system is generated in the middle of a reaction. So I've already given you a lot of other scenarios, right, where an allylic system could be generated in a reaction and how it gives multiple products. This is just another version of that. There is actually a way to control, as in this particular type of scenario, which pathway is more dominant as far as the 1-2 or the 1-4 product. That's because the 1-2 addition is going to be less thermodynamically stable than the 1-4. So if you lower the temperature and you are using kinetic control, you can get the 1-2 addition. But if you're at room temperature, you're going to more likely get this 1-4. So that's more likely to be in that other flipped state. Again, this is just showing you the two, starting from your starting reactant to the midpoint in which you have resonance, and then getting to your product. This point right here can be controlled using temperature, is what this is showing. All right. Basically, same concept. Here's a diene. Okay. We're adding HBr, and it has shown you one of the products. We are missing the 1-4 product. This is the 1-2 product. So good job on correctly identifying which product it is. If you note, it has added to this double bond right here. Okay, the 1-2 product. So what would the other product look like? This is the 1-2 product, but what would the 1-4 product look like? If you're unclear, just like memorizing, that's what it looks like. It shifts to this. You can always just think about what happens during this process and draw the two cations. That's what I like to do. So remember that the first version has a positive charge here. So think about what the other version would look like. That would be the positive charge and the double bond are gonna shift with each other. Like this. See how the double bond has moved into what it looks like in the middle of this system. So these are the two versions that can exist. And then if you just think about adding on your halide, where the positive charges are, it'll show you the two products. One product is this, that's going to come from this resonance form. If we add bromine to the positive charge here, you get this resonance form. And if you add it to this one, you get this resonance form. I'm just noting to think about doing that because some people, they memorize this concept of 1-2 and 1-4, and they just slap, a bromine on the 2 position or a bromine on the 4 position, but they don't remember that the double bond is also moving. So if you were to just put a bromine here, but not move the double bond, that is not the correct type of Yeah, I'm noting to think about what is actually happening as far as the resonance and how it generates the products, and not just go based on the numbers 1, 2, and 1, 4, because you also have to remember that this double bond moves too. So you're not just putting a bromine on the 2 position or the 4 without moving. For the 1, 4, you have to also have resonance movement of that double bond. See how it's in the middle here instead of on the end here? Because during the resonance process, the cation flips with the double bonds.
So they switch position.
Yes, they're resonating positions. Again, when you have an allylic system generated, you always have those 2 versions. That's what we've been seeing in all these cases. There's always 2 products, right? 2 versions. This same idea, same concept, also for addition of just straight halogens. So I just showed you a hydrohalogenation. That's where we're adding hydrogen and a halogen. Our hydrogen was kind of disappearing in our thoughts because we don't usually draw it, but we added a hydrogen that generated a cation, and then we added the bromine or whatever our halide was. When we add that, we generated the 2 different products, right? Additions of just straight halides through halogenation also can generate 2 products. Also because there is a 2-step process during the addition, and if you have a diene, you also, same concept, except now we're doing two halogens instead of a hydrogen and a halogen, okay? So you also get 1, 2, and 1, 4 mixtures here. In this case, for halogenation, the 1, 4 product is also dominant in most cases. Just like in the hydrohalogenation, I showed you that at room temperature, 1, 4 is also dominant. You have to cool down, you'd have to cool down the reaction to get the 1, 2. So notice here, we're always adding, for example, bromine on one end of the double bond, that would generate a cation. We have our resonance, and then you can get your second bromine either on the 2 position or on the 4 position. All right, we have a bunch of different dienes here. Which of these would undergo 1, 4 addition with our halogen bromine? So I want you to think about, what kind of system do we have to have for this to happen? What kind of diene system do we have to have? Not high temperature, but what's conjugated. They have to be conjugated, right? If they're too far apart, then you don't get this overlap. So that's your hint right here. Which one do you guys think? One on the far right? Did I hear that? Not just that they're the closest, but they're conjugated, right? Double, single, double. Notice they're the only ones in which you have double bond, single bond, double bond. That causes the conjugation, right? Yeah, they might be what looks like to you as sideways, but it is a double bond, single bond, double bond. That is conjugated right there. These 2 have too far apart, 2 single bonds, same here, 2 single bonds, same here, 2 single bonds. They're not conjugated. So on any of those other ones, if I were to do an addition, yeah, you could still do an addition reaction. It's just that you're not going to get resonance and make these 2 products with the 1, 2 addition or 1, 4 addition. You just have to get the conjugation where it's double bond,
Maybe I'm-
single bond,
maybe I'm missing.
double bond. What I just said, double bond, single bond, double bond. It has to be alternating double, single bonds. In a system where there's only two double bonds, you just have to have one single bond between them. Conjugation in general just means that you have to have alternating double, single bonds. You can have a lot of them for conjugation, but they have to be alternating, double, then single, then double, then single, then double. All right, so this is actually what we were looking at, and line is a little bit gone, but let's think about what the products would actually be here. So we're gonna do a bromine addition. Essentially, you're gonna open up this double bond and grab a bromine to start with. So you'd have a bromine on the end here. And that would generate a positive charge here. No more double bond there either. Just think of this as this is a single bond now. Okay, that's our first addition of bromine. So for the second addition of bromine, remember now I have generated an allylic system. You guys see it, right? Positive charge next to a double bond. Which means that there is another version of this compound that can resonate between. That looks like it's double bond, and the positive charge can flip, meaning I get double bond here, positive charge down here. So now second step happens, and I'm going to add my second bromine where the positive charge is on each of these versions. Oops. And that is going to give me either this, which would be one of the additions, or, sorry, I'm making this a single bond again, this. So which one is which? The one on the left, which addition is that, version is that? 1,4 addition. And then so the one on the right is the 1,2 addition. All right, so I promised you that we're going to talk about some other fun reactions about dienes. Just to pause for a second, what I just told you all about were all of the versions of those allylic systems acting special, because when they are generated, you can have more than one product if they're generated during a reaction. So I told you what an allylic system was, when it can happen, why it has stability because of that conjugation, that resonance. And then thirdly, I gave you a couple examples of reactions that during the reaction, they can generate one of those allylic systems and cause a scenario where you have more than one product. Okay, that was kind of the summation of all of those things. This is another type of reaction of a diene. I just want to stop on that. And it does still involve resonance. There is resonance happening, but there's a little bit of a different scenario going on here. This is a really, really important reaction called a Diels-Alder reaction. In chemistry, it is one of the few reactions we have that forms rings. So you can imagine, really helpful for us. This occurs when you take a diene, I already said, talking about diene, so double, single, double bond. And I kind of hate that they use this word, but what we're going to call a dienophile, which is just supposed to mean something that likes a diene.
Like,
Like a nucleophile, yeah. Something that likes a diene. Really, what this has to be is, as it's shown here, it just has to be one single double bond. One double bond. Okay, that can have whatever else on it. It's showing you, oh, it has A, B, X, and Y on it. We're going to talk about those parts of it, but a diene that's conjugated has to be conjugated diene. Double bond, single bond, double bond, conjugated diene, and some alkene. Two separate things. They can do what's called a cycloaddition. Technically, this is an addition reaction that's doing a 1,4 addition happening through resonance. But ultimately, what's happening is when these guys get close together, they can have a resonating addition reaction occur in which the double bond here, you can think of it as it's going to share its electrons and form a bond right here, causing resonance that then lets this double bond form a bond right here into a ring. I'm going to erase all my marks. You can actually see the arrows here. Follow the arrows. This double bond shares its electrons, forming a new bond where those dotted lines are. Right, where those dotted lines are. That then causes resonance to occur. These shift here. These shift here into space and form a new bond, ultimately forming a 6-membered ring. You start off with a total of 3 double bonds. You end with a total of 1 double bond. Notice where it is. It's in the middle of where our diene needs to be. And you now have a 6-membered ring instead of 2 separate things. Just a quick note on here. Remember how I talked about the S-cis conformation and how it was special? Look at how our diene is shaped. Notice it's in that kind of C shape. That's the S-cis configuration. It has to be like that to do this reaction so that it can then form a ring and line up correctly. All right, so I'm going to give you a couple rules now about the Diels-Alder reaction. One really cool thing about the Diels-Alder reaction is that it is generally pretty spontaneous if you get these two things together. If you get a conjugated diene next to another alkene, you can just start making some rings. That's why, again, super useful reaction. You do have to heat them up in a organic solvent, but generally this is a pretty spontaneous reaction and again, very useful. You can take any system that has a conjugated diene and any system that then has another random double bond and make them fuse together into a ring. There's lots of different examples. So the imagination of what can be decorated on these things is wide. That I think throws some people off because you see this first example here and you're just thinking, I'm always going to have something that looks like this with this, and that's it. But you have to be a little bit more imaginative and just think about if there's a conjugated double bond and there's another separate double bond, they can form together in a ring. I'll show you an example down here. This right here, malic anhydride, this is a ring, right? It has a double bond. That double bond can act with a diene and form another ring. So again, it can be any random alkane or alkene with any diene. I'll show you more examples. We'll actually see examples of that. depending on what is attached to what we're calling dienophile, the diene or the alkene by itself, will actually help expedite this reaction or slow it down depending on what they are. This is just showing you, as I noted, about it being in the cis trans or the cis S-cis configuration, excuse me, versus the S trans configuration where it needs to be in this curved configuration to undergo the Diels-Alder reaction. All right, let's look at an example here of a Diels-Alder with some fun dienophiles. So here is a cyclopentadiene. Do you guys see the diene here? So we're going to focus on this part right here. That's the diene, right? If I take this and I add it with dimethyl fumarate, do you guys see the double bond? That diene and that double bond can combine into a 6-membered ring. You can see what it looks like in our products just really quickly. Whoa, what is happening? Well, what happened is I formed a ring on an already existent ring. That's what happens when you form a ring on a ring, you get a fused ring. To try to imagine what you're seeing here, hopefully I can kind of highlight it again. Here was our original diene. That's, notice, a 5-membered ring. 1, 2, 3, 4, 5. That is our original 5-membered ring. It looks like this. The diene part of it reacted to form a 1, 2, 3, 4, 5, 6-membered ring. That's the 6-membered ring that formed from the diene and the double bond combining. Notice that they kind of just flipped this part right here that wasn't part of the Diels-Alder reaction up, and they reacted into a 6-membered ring. Yes.
So like if I was that dienophile, like I would have been like, okay, it's not that's this
The dienophile or the diene?
on that.
The diene isn't an S-cis because look at how the double bonds are. See how they're C-shaped to each other? Yeah.
Initially, it's like
Not you're looking at the dienophile, not the diene. The diene, that's the 2 double bonds. That has to be in that C shape.
all the time.
The diene, yeah, not the dienophile. What they're actually showing in this picture is that depending on this double bonds configuration, so one of them is trans and one of them is cis, does affect the configuration of the product. You can actually see that the end caps here, which were trans to begin with, are still trans in the product. And here, the end caps of the dienophile, which were cis to begin with, are still cis. I know there's a lot going on this slide after introducing the Diels-Alder reaction. Diels-Alder reactions are a lot, but let's do a practice. Okay, I purposefully gave you a complicated one here so that we really can see all the stuff going on. All right, first of all, I want you guys to tell me which of these is the diene and which is the dienophile. Which one's the diene? The one on the left, I heard a lot of people, that's this guy, okay. I am first just gonna redraw this to be in its proper configuration, which has to be S-cis, okay? I am not changing the molecule, I'm just rotating the molecule. It's just gonna help you see, like I said, they gave it to you in a hard. This example is purposefully hard.
Let's say where it was, molecule adjusts itself,
Well, molecules are all rotating.
so it's not,
It's just
oh.
it's just rotating constantly. So at some point in time, it exists like this, and at some point in time, it exists like this. It's just, I'm just pointing out that it has to be in this existence to undergo this reaction. I'm also just drawing it like this because it's gonna help you visualize. All right. Now, we know that the other thing has to be the dienophile, right? But I want you to tell me specifically what part of this molecule is actually going to be involved in this ring formation.
Where the zero goes, to the double bond over the, is that oxygen? To the fluoride?
The double bond, is that what you just said?
Yes.
That's connected to the chlorine.
Like going that way? Quadruple?
So generally, what I would just say is it's the double bond. Yeah. I mean, yeah, this right here.
I'm trying to make sure I.
Yeah. Yes.
Well,
I didn't say anything about that. So what this would, if you're, I'm actually not gonna get into the numbering of this one because it's past where we have gotten to yet. It would be, the double bond would be 2. But that's because I would start numbering at that double bond oxygen as 1 and then over to the left as 2. You will see why later. We haven't talked about how you deal with those functional groups and how you number them, but yes, the double bond would be 2, but you wouldn't start numbering from you wouldn't start numbering from down here. You'd start numbering right here. Anyway, like I said, don't worry about that right now. You guys, we haven't seen numbering those compounds. Okay, that double bond is what's involved, right? What I'm gonna do initially is I'm just focusing on these parts, putting them together, and then we'll kind of fill in. Right, so this double bond is going to react with this diene. And if that were to happen, you'd have your double bond here, right? There's my chlorine and this guy. Where's my, okay. All right. So this double bond, this diene, right? The double bond is what sparks this. It generates 1 new bond like this. That moves in here. And then it's actually a whole sequence of events where it's like move. And then this makes the last double or the last single bond. So what you end up getting is a 6-membered ring and your double bond moved there. These bonds, though I stretched them out right now, but those are newly generated bonds. But you can see the double bond or the 6-membered ring that is now generated is here. You guys see that? Okay. How are these 2 things oriented? We have actually, can anyone tell me what the name of that functional group is quickly? Type of functional group on the end here. Ester. This is an ester.
Don't put that. That was my first guess.
It's okay.
I didn't say it though.
Okay. Ester and a chloride, right? Down here at the bottom. How are these oriented? on the ring that now exists after our Diels-Alder. Trans, see how they were trans to begin with? Look up at the top, see how the chlorine and the ester. Oh, sorry, let me. You're right, okay, see how this and this are trans from each other to begin with? So in the end, on the ring, they are also trans. You can think about this as being one up and one down, but they end up still being trans to each other. They started off as trans, they still are. All right, so I'm gonna throw another wrench in this, in the Diels-Alder, okay? You can have a Diels-Alder reaction happen within the same molecule. What? Here's an example. I have a
Wait, compound or molecule?
same molecule. I mean, we're saying the same word. This is a diene. Do you guys agree? Conjugated diene right there at the end. At the end of the molecule. All the way over here is a lonely one single double bond. They are all attached to the same molecule, but this molecule is technically long enough that it can curve itself. And this end, at some point, can talk to this end if it were to bend. And if that were to happen, you could have a intramolecular Diels-Alder, meaning that one whole molecule reacts with itself, creating a reaction in a Diels-Alder. Here you can see what it would look like if that whole chain was bent. It's just showing you bent. Here is the double bond on one end. Here is the diene on the other end. They can have a reaction that forms a 6-membered ring, forming this product right here. This is a now bicyclic compound. I want you guys to notice that a little bit different than our example here. When you start with a ring and you do a Diels-Alder, you get what looks like kind of conjoined rings. See that product here? When you start with something that's a ring, but they're two separate things still, right? Two separate diene-O-file are separate molecules, but if one of them is a ring, you end up getting this conjoined looking ring. This case is slightly different. Notice that when it's one molecule reacting with itself, you make this bicyclic, meaning it's two rings that are just sharing a joint, but they're not kind of like intersecting with each other. Does that, you guys get what I'm saying? The difference here? I'm talking about this, like I said, these are super, super useful. Diels-Alders do get used a lot. In particular, I gave you this example because we actually do a lot of intramolecular Diels-Alders because those bicyclic rings are seen in biology a lot when you have those, especially two 6-membered rings next to each other. An example of this very quickly also happens not only chemists doing synthesis, but it happens in biology too. Diels-Alder reactions occur naturally, in particular I'm showing a picture here, and the Latin word, Pleortis austertus, which is oyster mushroom. My bad pronunciation. Oyster mushrooms naturally form lovastatin, which, by the way, statin, if you are at all familiar with anyone who has high cholesterol and they have to take statins, this is a very, very, very important drug that is making lots of money for some pharmaceutical chemists. But statins are naturally formed in oyster mushrooms, and part of the biological formation that occurs naturally in the oyster mushroom involves Diels-Alder reactions to actually take a chain and then make these cyclic rings. All right, now in Orgo 1, we started to talk about retrosynthesis, which was this idea of thinking backwards, right? And I just showed you how a Diels-Alder reaction works. You also can think about the reverse version of this, taking apart a 6-membered ring into its diene and dienophile to think about what materials you would have had to start with to generate that particular ring. Notice that if we're talking about the product of a Diels-Alder reaction, very specifically, what does the product of a Diels-Alder reaction have to have in it? After you're done with, what would you have? 1 double bond and what's a 6-membered ring, right? It has to be a 6-membered ring because of the diene and the dienophile, the very specific overlap that they have to have, it's going to form a 6-membered ring. Also, it has to be 1 single double bond in that 6-membered ring, right? So 1 double bond in a 6-membered ring. If you see that, that means you could form it with a Diels-Alder reaction. And you can think about kind of working the opposite way. Think about where the double bond is, that's where the diene used to be, versus the opposite part of the 6-membered ring being the dienophile. Here's a example of that, where we're noting our 6-membered ring here. How could we make this particular compound with this 6-membered ring and a single double bond in it? Well, we can imagine that this part had to be the diene in the past, and this part had to be the dienophile in the past. Everything that was attached to it. So you could have started with a very simple, essentially naked diene, and this 5-membered ring here that has a double bond in it as your dienophile. All right, so yes.
Oh, sorry.
Oh, okay. So on that note, same idea, think about how we could have generated this product using a diene and a dienophile. Okay, we're going to draw out the 2 things. So where did the diene have to exist before? Far left, where what is? Where the single double bond is. So I'm going to just highlight, right? This part used to be the diene, right? So I'm going to draw that by itself over here. And it was a diene, so it used to have 2 double bonds in it, right? Okay, what part was the dienophile? The right part, and it's just the 1 bond, right? Because during this cyclical process, we formed some bonds. So make sure you don't accidentally include those in your final product. This right here only was whatever is directly attached to it was the dienophile. So it's just that 1 part, and we have a little ester here, like this. And we used to have a double bond here. Don't forget to draw that for me too. So that's it. If you have these 2, notice the parts of the 6-membered ring that got formed during the process are right here. And so when we're thinking about the opposite, detaching those are disappearing. Right? Those are the new bonds that formed from the double bonds that we lost. Oop. It's the same one. All right, I'm gonna do one more. I know we're at 6:50 right now, but I'm just gonna do one more example on the Diels alder and thinking backwards. You guys, do you have homework questions on this? That's why I want to do this one. Again, where we see a 6-membered ring, right? Everybody sees it. Where was the diene before? On the left where the double bond is, right? So right here was our diene. Everything that is attached to those lines, I'm going to draw over here by itself. This used to be a diene, 2 double bonds, and it had a little guy on it, like this. And then our dienophile, right, is right here. Now, there is something here. There's some stereochemistry being drawn here. The 2 side things that are attached there, what configuration are they in? Trans. So I have to also draw them trans here. So I'm going to draw one going this way and one going this way. Okay, that is a key thing to note. Remember, I said also thinking the other direction, when you do a Diels alder, this dienophile's stereochemistry is retained. So we have to think about drawing it as well. I'm also pointing that out because I know your homework questions have some stereochemistry in them, so don't forget that stereochemistry. And this all the way over here. Okay. Really badly drawn. Sorry. I will have my pen next time, I promise. Everybody agree with this? Missing anything or? All right. So that is indeed how that's the 2 compounds you would need to generate this. Oops, this reaction on a Diels alder. All right. All right, well, I will stop there. I won't take up too much. I went 3 minutes over, so. Yes. Yes, we can. Let me type it in. That is a good question. So thinking back to just addition reactions of alkenes, it's going to want a more substituted product. So whatever results in there being a more substituted addition. I think almost all the examples you guys will see give you a pretty clearly symmetrical one though. Great, any other questions from you guys? All right, those of you in lab, we're just gonna quickly go upstairs and I'll have you just check out your drawers. You can kind of see this space, get used to the space, but we don't actually have any lab after that. So it'll probably take us just 10 minutes or so, 10, 15 minutes. Yeah, of course.